So why are we studying proofs in linear algebra? There's several reasons. First of all, it's one of the first upper level math courses that is required for all math majors. It introduces some good abstract mathematical objects such as matrices, vector spaces, and linear transformations. And it's good to understand kind of more formal mathematical proof when studying objects like this. The objects do give us meaningful structures about which we can write proofs, so it kind of is a good place for us to be working with writing proofs. We also have a lot of deep theorems that sometimes come up in other courses, but also are just nice to study within this course and that we can build on in this course and understanding proofs of those theorems and how to prove other theorems based on them or corollaries or other statements is important. Finally, learning to read and write proofs helps us communicate mathematical ideas clearly and logically, and that's important in all math classes, but especially an upper level course like linear algebra. A little more generally, why do proofs matter? In order to do mathematics, we must be able to talk and write about mathematics. A lot of students up till now have mostly been doing mathematics by finding numerical answers to problems or solving problems in a calculus class relating to functions, very much more computational. And we will do a lot of that in this linear algebra course, but it's nice as we move toward more advanced and abstract mathematics to work on writing and proof writing in particular. The primary goal of mathematics is to establish general mathematical truths, and the agreed upon way to do that is through formal mathematical proof. So how can we know whether a mathematical statement is true? We construct arguments called proofs. These establish the truth of mathematical statements. So we're going to be learning in this course sort of an introduction to how we can do that. In mathematics, an argument is not a disagreement, it is logical justification. So getting into some of the topics in this introduction to writing proofs, let's define what we call a statement, which is a declarative sentence that is either true or false. So let's go through some examples. We're going to determine whether each sentence is a statement. So basically, again, is this a sentence that is either true or false? So the first one, 2 plus 3 equals 5. We don't really care right now whether these are true or false, but just, whether they are statements. And this is a statement because we can determine if it is true or false. This one does happen to be true. 2 plus 3 does indeed equal 5. Please close the door. This one is not a mathematical statement. This does not have, sort of a truth or falsity to it. It's really just a declaration. Please close the door. X plus 1 equals 4 looks more mathematical, but again, this one is not going to be a mathematical statement because whether it is true or false depends on that value of X. And so this sentence as written is not a statement. All rectangles are squares. This is a statement. It is a false statement, but it is a statement nonetheless. So it is not true that all rectangles are squares, but we can determine if it is true or false. And that is kind of the key distinction here. And then Baltimore is the capital of Maryland. This is also a statement. This one is true. And then what time is class? This is a question. This is not a statement. You might be able to answer this question, but it is not a statement. Moving into variables and statements. So the sentence x plus 1 equals 4, as we said earlier, is not a statement because it contains a variable. Depending on the value of x, this may be true or false. We can turn it into a statement by specifying the variable. So for example, we could say x plus 1 equals 4, where x equals 3. This is a true statement. We can also quantify over the variable. So for example, we could say for all values of x, x plus 1 equals 4. This is a statement and it is a false statement. There are some values of x where this is not true. In fact, most values of x, this is not true. Moving into what are called molecular statements. So if we have just sort of an individual statement, we might call that atomic, but we can build more complicated statements from these simpler statements using logical connectives. So an example could be all Stevenson students study applied mathematics and 6 is a prime number. This statement is built from two smaller statements connected by the word and. So the two statements being that all Stevenson students study applied mathematics and 6 is a prime number. Those in and of themselves are statements, and then they are connected here by that word and. The truth value of one of these molecular statements depends both on the truth value of the smaller statements as well as the logical connective being used. So we're going to study what that means a little bit later.